So when you are doing curve sketching, there are three functions that have certain values that they cannot accept. So the three functions you have to watch out for are the square roots, the rationals, and the logarithms. I'm just going to use ln because we use ln all the time. Now, when you're working with these, or any function that contains these as one of its pieces, there will be places on your graph where there is no function. So for example, the square root, or the radical family in general, doesn't work if you have any x less than 0. 0 is okay, because the square root of 0 is 0. That one has an answer. But anything less than that, any of the negative numbers, can't go in there. And if you do a quick sketch of what this looks like, the radical has a little nub at the origin, and then it takes off like that. So there's function all over here where x is positive, but there's nothing on that side. So if you have a function like that, then what you're going to end up with is a hole, right? A chunk of the x-axis where that function doesn't exist. The rational function is good for positives, it's good for negatives. The one thing it can't accept is that x cannot equal 0. And so if you sketch that one, the rational looks like this, your xy axis, and then you have a curve that has an asymptote on the y-axis, because this curve cannot cross this particular value. And so what we've got there are two very different ways that functions fail. You can see that for this one, there's a whole range of places where the function doesn't exist. And for this one, there's only the one value. So this thing up here, where you have multiple x values that don't work, is called a domain error. Now you've done domain and range before. Domain is a set of x values or a set of inputs into your function. So if you have something like this, there is a set of inputs that will provide an error, and because it's a set of them, not just a single one, we call it a domain error. And what it looks like is it looks like a hole or a gap. Looks like a gap in your sketch. So you can see that here, all this space over here, where there is no function. The rational only fails at one place, and that one place happens to be the boundary between x as being positive and x as being negative. It also happens to be the boundary between this downward section and this upward section. So the idea of boundary is that there's one value that splits the function into two pieces. And it may work on one side or the other, or it may work on only one, I don't know, it depends on the function. But if it's only a single place where it doesn't work, you have a boundary error. And a boundary error looks like an asymptote, a vertical asymptote. Okay, so comparing these two functions then, the radical has a domain error, but no boundary error. You notice there is no asymptote there. The boundary between where it works and where it doesn't, right, when x equals 0, is perfectly fine. The rational doesn't have a domain error. It's okay in the negatives, it's okay in the positive. It's just a problem on that boundary between the two regions. A function like ln, on the other hand, ln cannot accept any x that is less than or equal to 0. Notice there's a difference there. The domain error required a less than symbol. The boundary error required a not equal symbol. And this one required a hybrid of the two. If I were to quick sketch ln for you, ln passes through 1 on the x-axis and it has its vertical asymptote here, and then it takes off like that. So you notice that you can't have any x's that are less than 0 because there's a gap, just like the radical had a gap. You also have a vertical asymptote because the boundary itself between where it works and where it doesn't also fails. So ln has both a boundary error, or both a domain error, and a boundary error. So not only does it have a section of the x-axis where it doesn't work, but that place that defines the line between where it does work and where it doesn't also fails. And you can see it in the form of a vertical asymptote. So if you're trying to sketch a composite function and it contains a radical, then there's a very strong possibility that there will be a chunk of the x-axis where you cannot draw that function. So you just leave a hole. If you see something with a rational, right, something in the denominator of a fraction, you should be expecting to find vertical asymptotes. And you did a lot of that in advanced functions, trying to find the vertical asymptotes of rational expressions. When you're sketching anything containing a ln, you should expect both. There should be some vertical asymptotes somewhere, and there should be regions where the function doesn't work, depending on what's been shoved into that argument there. So I'm going to erase this, and then we'll do some slightly more complicated examples. So if you were trying to sketch this function, what you need to be able to do for this section, right, hunting for errors, is to spot that there is a piece here of that function that is one of the three functions that causes domain and boundary errors. You have to remember that for ln, you get the boundary error when the argument of the ln, so this in case it's x minus 5, whenever that is equal to 0. So that will be when x equals 5. That's going to look like a vertical asymptote. You have the domain error any place where this argument is less than 0. So if I kick the 5 over there, it will be for anything less than 5. So when I go to sketch this thing, 1, 2, 3, 4, 5, there will be no function over here. What I'll end up with is probably some sort of asymptote, like so, and then nothing on this side, because this is less than 5 over here. So the function will show up only on this side of that asymptote. In order to make sure it's an asymptote, you should always try and put the 5 back in there and see what you get. So in that case, you'd have f of 5 equals 5 squared times the ln of 0. Ln of 0 doesn't really have a value, but it approaches negative infinity. You look at this particular thing, and you see that that is not an indeterminate form. 25 times infinity would be negative infinity. So your asymptote is confirmed. Smiley face. All right. Good. So when you go to sketch this thing, after you've done your x-intercepts, your max-mins, your points of inflection, your end behaviors, all that stuff, you should make sure you also end up having this vertical asymptote when x equals 5, and that there is no function drawn for anything less than 5, because that is a domain error for ln. I'm going to erase this and change it just a teeny tiny bit. I'm going to change this to just x squared ln x. So what does this change about this question? Well, it won't be x minus 5 here anymore. It will be x. So that means that x is 0 at the boundary error. And this won't be a 5, so this is just x is less than 0 for the domain error. Which means in this little sketch, instead of having the asymptote at 5, the asymptote is showing up on the y-axis when x equals 0. So this is the bad spot. This is where the asymptote might be. Might. To confirm that asymptote, I should take this x value and I should pop it back into the function. So I would have f at 0 is 0 squared ln of 0. Ln 0 doesn't really have an answer, but it approaches negative infinity. Now this is where I get into problems. 0 multiplied by infinity is a thing called an indeterminate form. Let me write that word for you. Indeterminate form. Now, you may have discussed the indeterminate form in advanced functions when you're thinking of limits. If this happens to you, you have to actually manually calculate the value of this limit. So here, this isn't correct, right? Like you can't put a 0 into a ln, but what you can do is take the limit of x going to 0 of x squared ln x. So that's a legal maneuver. And so the way you do this manually is you try some x's that are getting close to 0 but not quite. So if you let x equal 0.1, you would have 0.1 squared ln of 0.1. And if you pop that into a calculator, 0.1 squared times ln of 0.1, you get negative 0.023. And if I try another one, 0.001, that would be 0.001 squared multiplied by ln of 0.001. I get, goodness, negative 0.000000691. And as always when doing limits, you should do 3 because 2 points are not enough to confirm a pattern. I'm going to add 4 more zeros on there. 0.00001 squared multiplied by the ln of 0.1234001 gives me negative 0.00000000015. Okay, now if this were an asymptote, these numbers would be blowing up to infinity. As I crept in closer to that vertical asymptote, these numbers should be going -2, -2,000, -2 million as the asymptote slides down the y-axis. That's not what's happening here. These numbers are approaching 0 from below. You notice that they get closer and closer and closer to 0, and they're negative, so they're coming up to it. Approach 0 from below. So, what happened here? Well, I was hunting for boundary and domain errors, and I identified a piece that would normally create a boundary error at that particular spot. So I noted it, but then I had to confirm it by feeding it back into the function, and I got an indeterminate form. And when you get an indeterminate form, you have to take the limit manually in order to confirm or refute the fact that that's an asymptote. And so that happened here. This boundary error ends up being masked by the x squared. And to put it in a slightly more ridiculous way, this 0 is more 0 than this infinity was infinity. So when you let the two of them fight, the 0 is the one that wins. So I can scratch that off my particular function here. There is no vertical asymptote there, but the domain error remains unaffected. This function, even though the boundary error was masked because of the other puzzle pieces involved, this x squared is not powerful enough to give ln a value in the negatives. So even though the boundary error was collapsed, the domain error remains. So this function, when you try to sketch it, will have nothing on the left side of the y-axis. So if you were asked to sketch this function, you'd look at it and you would see that it does in fact contain one of these functions that creates boundary or domain errors. So I'm going to have to test that. I'm going to have to remind myself that I get a domain error whenever the argument of a radical is less than 0. So if I pop the 8 over, I get this. So I'm going to end up with a domain error for any x less than -8. So when I sketch this thing, wherever -8 is, 3, 4, 5, 6, 7, 8, from this point over, there's nothing on this graph. So your function basically starts at -8 and goes this way. I don't have to worry about checking boundary errors for this one because the radical doesn't produce boundary errors. So it's not an issue for this particular example. Okay, so for a function like this, ln of x squared minus 1, ln produces both boundary and domain errors, so I have to check them. It will have boundary errors whenever x squared minus 1 is equal to 0. So that would make x squared equal to 1, so x would be the square root of that, which is plus or minus 1. Feed those back into the equation to test it. The function at 1 would be ln of 1 minus 1, which is ln of 0, which doesn't have an actual answer but approaches -infinity. And you notice there are no other pieces. There's nothing multiplying this infinity to create the indeterminate form. So this boundary error stands. If I changed it to -1, -1 squared is just 1, 1 minus 1 is still 0, and this still goes to approaches -infinity. So that boundary error also stands. So I don't have any indeterminate forms telling me that this thing doesn't count. So in it goes. I will end up with domain errors for this one. Sorry, let me be clear. There will be vertical asymptotes. Vertical asymptotes at x equals plus and minus 1. As for the domain error, this is true any place where x squared minus 1 is less than 0. So x squared would be less than 0. And you have to ask yourself, sorry, x squared has to be less than 1. You have to ask yourself a bit of a question here. What about 0.5? Is 0.5 squared less than 1? Yes, it is. So, in fact, anything that's going to be less than 1 but more than 0 is going to fail. Try the negative decimals. So like -0.9. -0.9 times -0.9 would be positive 0.81, which is less than 1. So this is going to fail all the way down to -1. This range between -1 and 1, which happen to be your boundaries, and that is not an accident. That this place between your boundaries has no function to it. So if I were to sketch this, I would end up with a vertical asymptote at +1, a vertical asymptote at -1, and a function that does something outside. I saw that these go to -infinity, so these are going to -infinity here, like so. And then this function does something like that. You can pop it into Desmos if you don't believe me. Or later we're going to do some calculus on it to prove that it has no max mins or points of inflection. So there you go. And you can see what's happening there is at this vertical asymptote at -1, it rides all the way to -infinity. At this vertical asymptote at +1, it rides all the way to -infinity. And there is absolutely nothing between those two vertical asymptotes because there is a domain error in this function that obliterates the function between those two values. So for this last example, e to the x multiplied by the radical of x squared plus 4, I recognize that radicals are one of those functions that create domain errors, and that domain error is going to happen anytime that x squared plus 4 is less than 0. So if I kick the 4 over here, I end up with x squared is less than negative 4. And now you've got to ask yourself another logical question. Can you get a number being less than negative 4 if you square it? Well, the trouble with that is no number squared is negative. And on a number line, if that's where 0 is, and this is where negative 4 is, there are no numbers past here that are squares. So this little condition here, this is actually impossible. Exclamation point. And so because it's impossible, there is no domain error. No domain error as a result of this radical. Basically what you ask yourself is there any place where the inside of that radical would be 0? And what's inside of that radical is a parabola, x squared plus 4, which if you sketch it is a parabola that's been shifted up 4 squares and then does this. So where does this parabola cross the x-axis? Well, it doesn't. So if it doesn't actually cross the x-axis, then there's no place where x plus 4 is 0. And if x plus 4 is never less than 0, then this thing can never manifest its potential domain error. So net, you need to be checking for either logarithms, radicals, or things in denominators. If you can satisfy the conditions inside the argument of those pieces that would create either an asymptote, boundary error, or a gap, which is a domain error, then your graph should have them show up when you sketch it. So in order to try and illustrate to you exactly what all of these things look like when you render them, I'm going to attempt a level 1 technological miracle. So there it is. So if I were to pop up the first function I've got on there, the square root of 25 minus x squared, that's what that says. Let me just write that down for you. 25 minus x squared to the exponent 1/2 is the same as the square root of 25 minus x squared. Okay, now that function up there, because it's a radical, it should generate a domain error anytime 25 minus x squared is less than 0. So if I bring that x squared over, I end up with 25 is less than x squared. And that's going to be true if x is more than 5, right? So if I made this 6, 25 minus 36 would be a negative. Or when x is less than negative 5. And if I were to pop that those ranges up there on the picture, then you'll see in the shaded areas off to the wings that there is no function there. You've got just the little arc, and then beyond negative 5 on this side it doesn't appear, and then above positive 5 on this side there is no function. So the boundary domain, or sorry, the domain error for that particular function ends up being anything past plus or minus 5. So if I switch to the next one, I end up with 1 over x squared minus 9. So let me just write that up for you as well. X squared minus 9 to the negative 1 is the same thing as 1 over x squared minus 9. Now that's a rational expression, and rational expressions are supposed to create boundary errors anytime their argument equals 0. So I should end up with a boundary error any place where x squared minus 9 equals nothing. So that would be x squared equals 9. So x would be the square root of 9 is plus or minus 3. And so if I were to take that picture and I were to add to it any place where x is 3 or negative 3, there we go. you can see that there is a vertical asymptote at +3 and another vertical asymptote at -3 that function happens to follow. Alright, so last but not least, we have ln of x squared minus 1. Let me write that down up here. Ln of x squared minus 1. Now, logs, or logarithms, be they normal logarithms or the natural logarithm, which this one happens to be, end up having boundary errors when the argument is 0, and domain errors for when the argument is less than 0. So I'm going to find those boundary errors first. When is x squared minus 1 equal to 0? Well, that happens, square root 1 is plus or minus 1. That's problematic when x is either 1 or -1. So I should have vertical asymptotes showing up there, and you maybe can see them now. You'll see it better when I throw the shading in. The next question then is this domain error. Well, the domain error should be contained by the boundaries. So if I were to check anything, I'm trying to figure out when x squared minus 1 is less than 0. So any place where x squared would be less than, keep doing that, less than 1. Well, that will happen any place between these boundaries. So that's -1 is less than x is less than 1. So I should end up with a domain error here. Should be a gap. And I should end up with asymptotes here. And if I throw the shading in there, there we go. You can see that there is indeed a gap in between that particular space where the function doesn't appear. And there are asymptotes at both plus and -1. So the last one we're going to do then, I'm going to clean this all off and I'll throw up a function that has all these pieces put together. So I'm going to put up there p as a function of x is 1 over x squared minus 9 multiplied by the square root of 25 minus x squared multiplied by the ln of x squared minus 1. So we did each of these pieces individually, but I'm going to put this function up into my magic square in a minute, and we'll see if all the features manifest. So looking at this monster, I can see that I have a rational expression, which should generate boundary errors, and I have a logarithm, which should generate boundary errors. So from this, I will have boundary problems, boundary errors, aka vertical asymptotes. I'm just going to write VA for now. That should happen when x equals plus or minus 3 because of this rational. And it should happen again at plus or minus 1 because of this logarithm. Thinking about the domain errors, I have two pieces up there that are going to cause domain errors. The first one is this radical. I'm going to end up with a domain error there for x greater than 5 or x is less than -5. So the function should stop in the wings at 5 and -5. I'm also going to have a domain error between -1 and +1 because of that logarithm. So if I were to squint real hard and make it appear on my level 1 technological miracle, you can see boundary errors at plus and minus 3. You can see boundary errors at plus and minus 1. And you can see that the function does not proceed beyond -5 on the left or above +5 on the right, and that it has that same hole between -1 and 1 due to the logarithm. Now this one's a monster. Trying to do the max, mins, points of inflection, etc. on this function would be bordering on impossible. So we won't be sketching one that's this complicated, but I like to put it up there to try and illustrate to you how you can force boundary errors to appear, or how you can force domain errors to appear, or what the pieces look like in order to generate those particular features.